All right, so today's presentation is about factors that affect solubility. You will find notes in Schoology for you to use for this. So let's just review some physical factors that we have that affect solubility. First one is solute-solvent interactions. We've talked about this, so this is all about IMFs, right? Our idea of like dissolves like. So polar substances tend to dissolve in polar solvents. Nonpolar substances tend to dissolve in nonpolar solvents, and interactions that are similar to those either way. Another factor we talked about was pressure. Pressure does not affect the solubility of liquid or solid solutes, but it does affect a gas solute like carbon dioxide dissolved in water. And what we find out is that as the pressure above a gas or above a solution increases, the solubility of that gas increases. And so as a result of that, if you keep a high pressure above a liquid or a liquid solution that's got a gas dissolved in it, that gas will stay dissolved. If you release that pressure or lower that pressure, the gas will become undissolved. This is the process that you see anytime that you open a pop bottle. You release the pressure that's above in the airspace above the soda. And once that airspace is released, the pressure above it drops, and that takes the gas that is dissolved, the carbon dioxide gas, and allows it to become undissolved because the solubility has decreased. We've also talked about temperature before, right? Solid solutes, the solubility will generally increase with increasing temperature. There are a few exceptions to that, but in general, we can go ahead and we can look at a table like this and we can say, oh yeah, we can see yes, as the temperature goes up, the solubility of those salts goes up. The effect on gases is the exact opposite. Again, as we increase the temperature, that increases the motion of the gas particles, which makes them less likely to stay in solution. And so for gases, as temperature increases, we see the solubility going down. So those are all factors that we've talked about before. So today and tomorrow, we're going to get into two factors that we've not discussed before because they have to do with equilibrium. And the very first one of these is called the common ion effect, which is what you learned about in your POGL today. So here's the gist of the common ion effect. If one of the ions in a solution equilibrium is already dissolved in the solution, the equilibrium will shift to the left and the solubility of the salt will decrease. Okay, so here's our standard solubility equation, but let's say instead of putting these into water, we're going to put them into a solution where there's already sulfate ion. Well, that in a sense says that we have increased the concentration of sulfate in this equilibrium just by putting it in there, and as a result of that, the reaction is going to shift away from this, and if it shifts away, that means it shifts towards the reactant side, where we have solid BaSO4. So some of that would have dissolved before is not going to dissolve. It's going to stay in the solid form. And so again, if we have a common ion in solution, it decreases the solubility because the equilibrium shifts to the left. Okay, and so as a result of this can affect our solubility calculations having to do with KSP. And so essentially, just like we did in the POGL today, you're going to go ahead and you're going to rice it. You're going to make sure that the concentration of the common ion is set as one of your initial concentrations. You're going to assume the concentration of the common ion is large compared to the solubility concentrations of the salt. That was that whole thing that we had in the POGL, where basically if your common ion concentration is much, much larger than K, then you can assume that the solubility of, or the concentration here is going to be way greater than whatever we get out of the dissolving process. And so essentially that stays equal. We'll see how that works again. And then it says check final concentrations versus assumption to make sure the assumption is valid. And we'll show you how to do that today. All right, let's go ahead and let's apply this with letter B. Okay. So we're going to go ahead and we're going to start off by putting in our dissolving equation. So CaF2 goes to Ca plus 2 plus 2F minus. Okay, so there's our reaction. Okay, our initial concentrations, again, we don't care about the solid. The calcium is hopefully going to happen when we dissolve. And the fluorine will also happen when we dissolve, but we've already got some fluorine from this ion in the solution. So we're going to have 0.010 molar F in there. Okay. Change according to stoichiometry. This is going to be plus X. This is going to be plus 2X. Okay. And then equilibrium. Okay, so equilibrium, this is going to be X, and this is going to be 0.010 molar plus 2X. So for this particular problem, again, we need to know the KSP for CaF2, right? And so we can put that down here. KSP is going to equal the concentration of Ca plus 2 times the concentration of F minus squared. And if we look that up in the back of the text, we can see that that number is 3.9 times 10 to the negative 11th. Okay, so we've got that then. All right, so if we look at that KSP, that's a very small KSP, especially relative to the 10 to the negative second that we have in our concentration of our common ion up here. And so as a result of that, we know that the dissociation of the dissolving process is going to result in very little F being produced. And so essentially, this 2X is going to make hardly any difference in the overall concentration here. So we can make the assumption that the equilibrium concentration is going to be essentially constant within sig fig squishiness. All right, so then that makes this problem fairly easy. Okay, by making that assumption, this becomes X. This becomes 0.010 squared. And that equals 3.9 times 10 to the negative 11th. So if I solve that for X then, we get 3.9 times 10 to the negative 7th molar. All right, and so then that is our value for X, which is our value for the Ca plus 2, which is related to this by a 1-to-1 stoichiometric ratio. And so there then is our answer. And if we were to calculate this without the extra thing, we would see that that solubility would be much higher.